Morning, everyone. Thanks very much. It's a lovely opportunity to present here at the conference today. Um, so my name's Pete Culmer. I'm Associate Professor at Leeds, and I run the Surgical Technologies Group at Leeds. So we work very closely between mechanical engineering and researchers there and the Leeds teaching hospitals. And this is just a bit of a preface because it kind of influences quite strongly the kind of research that we do and the applications that we pursue. I wanted to acknowledge up front, this is very much a collaborative effort, and in particular, a lot of this work is being driven by undergraduate internship students, which we're really proud of, so we've supported that within our group. So you can see some of their names here. So just to give you some background, the kind of work that our lab does at Leeds, we have kind of interest in the application of technologies to address challenges in surgical technologies and healthcare in general. So soft sensing is one of those themes, the interaction of sensing systems with the human body to assess and to modulate different behaviours. But also we're interested and have a focus on soft robotics, so the two kind of go hand in hand. My colleague Ali Alazmani has been working on soft cardiac assist devices. And we're also interested in modelling physiological systems. So you can see in the top right a model of the human rectum, as it turns out, being filled and distended, and we're looking to measure the pressures inherent within that and to observe those effects. So this kind of work influences the research that we do, that we're quite pragmatic in the kind of the underlying enabling technologies that we develop. So we were interested to support a lot of the work that we do and the clinical collaborations that we do. We kind of routinely heard that there was a sort of a demand for pressure sensors, but pressure sensors that could be fabricated fairly easily at low cost and that were physically very robust as well. And so we kind of set out to go down that line, to think about how we could develop in fairly basic lab facilities, high precision sensors that were robust and that could operate in conjunction with the human body. So you've got the motivation, the classic kind of bio-inspired approach of, look at the human skin. It's incredible in terms of its sensitivity and its robustness, highly versatile, and it's able to do a huge array of tasks, a high operating bandwidth, and it enables us to do a whole range of things. So we were motivated to look at sensors that could enable us to kind of look at human-robot interaction, and in particular design smarter surgical tools and instruments, many of which might be low cost and disposable. And our objectives were to look and see if we could mimic some aspects of the human skin in terms of the performance. So not all, but in terms of things like sensitivity or resolution and robustness, can we try and emulate the human skin and its capabilities there? There's clearly been a huge array of research in this field, and it seems to be ever growing. Every kind of month you see a new paper, and very high impact journals, and it's really kind of fascinating to watch the field explode, I guess. Sensory skins or e-skins, seem to be very much on the uptake at the moment, and we've just heard a lovely example of one of those. And I guess typically they kind of represent things that would require fairly specialized fabrication techniques, at least for us mechanical engineers. So we kind of looked firstly for some inspiration from some more mechanical modalities of sensing. So we've got an array here of just some examples of some nice versatile tactile sensors, and in particular our focus was looking at sensors which could detect not just a normal force or normal pressure, but multi-axis force and pressure. So Tactile is quite a nice innovative example. Uses optical sensing, so the deformation of a dome with dots on the underside can be detected by a small camera element housed inside. It's very robust physically, and it's able to detect and look at sort of deformation of that dome very easily. Things like Biotac and Tactile and now Optiforce have started to kind of cross over and to be commercialized. So there's clearly a lot of activity in this domain. So we were looking for, I guess, an approach that would enable us to sort of mimic some of this behavior, but maybe at a lower cost and with a bit more flexibility in terms of integrating it into medical instrumentation or sort of clinical applications. So we started off by developing a magnetic-based sensing modality. We call this MAG1. Now, other research groups have looked at similar kind of strategies. Here, what we do is couple a 3 degree of freedom Hall effect sensor mounted on a small circuit board with a silicon elastomer, and that elastomer modulates the applied force or pressure and changes the position of a magnetic element. So the magnet moves with respect to the Hall effect sensor, and if you then look at the Hall effect, the measured magnetic field, you can determine the forces that go into that system. So you can decouple the magnetic fields that are measured and then translate that back into the applied forces on the tip. So with a very cheap system like this, you're kind of looking in the region of, I guess, £2 to £3. You can produce a system which is very, very precise, has high sensitivity, and is very easy to fabricate in a conventional lab setting. We're essentially using 3D printed molds, taking elastomers, casting the elastomers, and then putting them on top of a chip. Then we do some calibration work, and then we get the resultant response that you can see here. So it's able to detect the brush of a feather. It's also very robust. If you hit it very hard, you're not going to damage it, although you may saturate the sensor output. Some of the complexities associated with this, though, are the non-linearities associated with it. And so we've spent a lot of time looking at calibration, which I'll touch on later, but also that this had a pre-programmed compliance. So you pick a particular elastomer. So here we use EcoFlex, and we maybe use 0020 or 30 for that dome. And you can optimize the dome geometry, and you can optimize the stiffness of the elastomer that you use, but only in fairly discrete levels. So, if you need to go from a soft elastomer, like EcoFlex, up to, say, a dragon skin, you've got quite a big jump in compliance. So what if we wanted to have a bit more of a nuanced sort of design freedom, I guess, for a particular application? That was our motivation. So we came up with the idea of, rather than having a solid dome, solid elastomer dome, why don't we make this a bit like a bike tire? Why don't we have this so that you can pressurize a small cavity and use that pressurized cavity to change the compliance, the mechanical compliance of your sensor? So to some extent, you decouple the compliance from the elastomer shell, or at least you allow yourself a bit more room to maneuver. So that was the kind of the working concept. The underlying principle is obviously, still the same. You have a magnetic element at the top of the sensor dome. Now, this can be on the underside, so it doesn't have to come into contact with something like the human body. And then you have your dome, which can be pressurized, and then the Hall effect sensor lies underneath. So that was our kind of operating principle. We set our internship students on a summer placement to design, optimize, and fabricate this, and then to present or to develop a paper with our postdoc team for this conference. So it was a really nice challenge and exciting project to kind of get stuck into. So we looked at some FE analysis. You can see here that the codes here are, this is Dragon Skin 30, Dragon Skin 20, EcoFlex 50. And we're looking at the change in the geometry of that sensor shell with internally applied pressures on the dome. So what we'd like to do is to achieve a different compliance without completely distorting this dome. Clearly, if it blows up like a balloon, it's not particularly useful for us. So we need to try and captivate that pressure. Now, we could use a constraining layer. So we could have some kind of inextensible outer layer on this sensor, but we really wanted to keep the fabrication technique fairly simple, fairly easy to produce. So we were looking to see if we could do that by structural optimization of this shell. And we eventually came upon a geometry that we found could give us a nice compromise between not having too thick a wall, so allowing us to have a nice low compliance, but still allow varying pressure. And then the fabrication process. So as I said, we're using very simple benchtop fabrication processes for this sensor. So you have a two-part mold, essentially. You use a standard silicon, you apply your spray release, pour in your silicon, cure the shell, and then at the end of it, you get your nice elastomer dome, and then you fabricate. So this is a custom board that we fabricated, but it just uses a commercially available 3 degree of freedom Hall effect sensor. So unlike the keynote today, which was incredible, but I'm definitely not a nuclear physicist. I won't pretend to be able to understand the complexities of designing things like Hall effect sensors themselves. I'm more interested in the application of those Hall effect sensors. So you fabricate this system, pull the compound system together, and then you can see our pressurization lines here. So one line is used to pressurize the cavity, the other line is for an active sensor, so we can record the pressure, and we can lock that off if we need to. So you can see our finished system here, and this system comprises the tactile sensor in the middle, and then, as I said, we've got a syringe to supply pressure, so you can change the pressure just by manually injecting that at the moment, and you can lock that off. So we have lure connectors, so we can just kind of inject, reach a predetermined pressure for a particular application, lock it off, and then we can also determine what the pressure is as well. This system here is the MyRio, so National Instruments make a system, just an embedded microcontroller essentially, and we use that to communicate with the Hall effect sensor here and to sample the pressure sensor. So the Hall effect sensor has the nice property that it uses I2C communications, so it's fairly quick, fairly rapid, but it's also very easy to interface with. And what we did then was we ran some tests to look at the change in compliance. So you can see if we pressurize the cavity by just slightly different amounts, we're able to change the gain, or the compliance of the sensor by a fairly notable amount. Okay, so we pressurize the cavity and then we lock it off so that there's a fixed volume within that system, and then we do essentially a deformation test. So we deform or distort that top surface by 0 to 5 millimeters. So we step through and then we look at the resultant force, and we can see a change in compliance. So when we increase the pressure, as you'd expect, then we have a higher resultant force, and it's up to 33% in this small range of pressures. So jumping from 100 to 120 kilopascals, it's 33% increase in the range of force that it can measure. So what we're looking to do is to kind of take this concept. This is an early proof of principle, and we're quite excited by its application for different areas of healthcare. One of the, I guess, the observations we've kind of noted of this system is that it's still quite stiff, and what we'd like to do is reduce the kind of the low level stiffness to something that approaches soft tissue, so you can really optimize its interaction with soft tissues both outside and within the human body. So to do that, I think we are going to have to move towards having a constraint layer to encapsulate this system, and then a small thin elastomer shell to encapsulate that kind of cavity. So we'll probably have to move to a slightly more complex fabrication process, but I think we can do that. At the moment, we're manually controlling the pressure supply, but I'd like to regulate that so you can dynamically change the compliance of the sensor to adapt to its environment. So that might have particular application in things like robotics, if you're looking at grasping things. So you might want to initially a very light touch, a light grasp, so you have a low compliance, and then as you hit something and you want to grip it more tightly, change the compliance of your sensor. So it's both a sensing modality and it's kind of interacting with an object. If I move on the slide, so I mentioned characterization before, and the complexities of calculating or characterizing this system we've looked at in a previous publication. So you have a tightly coupled system where you have your 3 degrees of freedom of your magnetic field, and you're looking to extract your resultant forces that have been applied. So you're looking to get the relationship between your measured magnetic field and then your output force. What we've done previously is use genetic algorithms to essentially take a bunch of calibration data and then to try and calibrate that system. So to use it almost like a black box approach, but look to develop equations, characteristic equations that are particular to a particular sensor. What we haven't done so far is included pressure. So it's obviously it adds another degree of freedom. So in the future, what we'd like to do is use some machine learning techniques to scale this so it can accommodate varying pressures and varying magnetic fields. There's also some, I guess, some limitations with the system you might have spotted. We have a 3 degree of freedom Hall effect sensor, and we have a magnet, and we're extracting the forces, so Fx, Fy, Fz. This presumes that the magnet stays normal to the Hall effect sensor. So in a small sensor, it's reasonably, it's a reasonably good assumption. But clearly for like large deformations, if I essentially twist the top of the sensor, rotating it relative to the Hall effect sensor, then that will be misinterpreted as a displacement. So that's something that we'd like to consider by having more than one Hall effect sensor underneath. So then you can detect those extra degrees of freedom and possibly look at doing torque measurement as well. And then what we're doing at the moment is actively looking for applications in healthcare and robotics. So we're developing a few leads at the moment, looking at things like osteoarthritis and splint use. So to see where we can use these low-cost sensors to inform clinical treatment and clinical assessment. Okay, I think that just brings me to time. So last but not least, I really should acknowledge the whole team. I'm just the person who comes up here and presents, but the people are doing a lot of the hard work. You can see rewarding themselves in a picture there. So our team of students, in particular interns from PSG in India, and colleagues at Leeds and Imperial College London have done a fantastic job on this work. Thank you very much.